Welcome back to the course on architectural design of ICs. So, today again we will continue the introduction part. Okay. So, in the previous lecture I discussed about different design styles of VLSI design or to build one integrated circuit. So, at that time I said that the semi custom design, full custom design, then system on chip and then programmable logic device. So, what are that means difference between this programmable device and ASIC is that ASICs are basically it gives you high performance, it consumes low power and this also low cost whenever you are producing or whenever you are designing it for high volume application. And this FPGAs is that this is the off the shelf, that means this is already pre-built. So, you can just buy it from market and then you can use it for your particular system design, and then it comes with low development cost, and it also gives you the flexibility of that means the primary objective of this FPGA or programmable device is that you can achieve the reconfigurability option. That means you have the scope or you have the that means chance to reuse those particular hardware for your design. That means whenever you are designing the particular hardware or particular system. And this also has the another advantage is that shorter time to market. Okay. Also you can achieve if you are using FPGA, but here the thing is that you are reducing the performance in compare with ASIC. So, if you see just this is one just example of this the difference between this ASIC and FPGA. If you see area wise, this this particular area, this is basically the area for one Xilinx Vertex 2 6000 series FPGA. So, this much of area you require, whereas the with equivalent functionality or the equivalent gate count, if you follow the ASIC design style. So, at that time you require only this particular area. Okay. So, that means this is 51x times higher if you follow this FPGA design style. So, at that time you are consuming 51x times higher area than if you follow the same design in ASIC design style. So, if you are following more area means it consumes more power and the more area too, that means it requires more cost or more power hungry device or power hungry system whenever you are following FPGA in compare with ASIC. Okay. So, this is just one example of that. So, here one slide is that regarding this VHDL versus Verilog. What is VHDL and what is Verilog? So, I am telling you about designing one system, or this VLSI design passes through this particular phase, but how you can describe the circuit. So, whenever you are using one tool, using this automation tool, whenever you are designing your system, so at that time the system definition language should be there. Okay. So, that is why there are hardware description language, that means it is there are basically specific language for that, by which if you use those language you can describe the hardware, or the tool will know that okay, this is this language, this hardware description language. So, this means that it is just like that means if you are you can speak with Tamil. So, at that time you will be know only Tamil. If I speak to in Tamil, so at that time you will understand what I am saying. If you are that Marathi, so at that time if I speak in Marathi, at that time only you will be get to know that what I am saying. So, it is something like that, that whenever I am describing the hardware, so at that time I need to describe the hardware using its particular language, which it can recognize that what I am trying to say or what I am trying to command the tool to do. So, this VHDL and Verilog, these are the very commonly used language for describing the hardware. So, this is the just the difference between VHDL and Verilog. Both are very popular. Any of these VHDL or Verilog, nowadays people are basically using System C or System Verilog. So, any of these language you know, and then you can use for your particular system design. So, then we will follow this design FPGA design flow, or this not specific to FPGA design flow. This is just if I say that VLSI design flow. Okay. So, VLSI design flow, in VLSI design flow there are little bit difference between this FPGA design flow and this ASIC design flow. So, in FPGA design flow, if I say, it has to start with these ideas, design ideas or this specification. Then you have to know about the detailed design or this RTL description of that particular things, or RTL means register transfer logic. Then you have to follow the functional simulation. Then after functional simulation, you have to follow the synthesis and implementation option. So, after synthesis and implementation option, you have to follow the timing simulation. So, one timing simulation is done, then you can go for device programming, okay, as you are following this FPGA design flow. So, here the thing is that this particular things will be deferred if I follow the ASIC design flow. At that time, I do not have any pre-built device. So, I can go for device programming. So, after timing simulation, what you have to do there, these things you have to do it manually. That means, you have to build your own ICs. So, at that time you have to build, that means you have to go for this map, that means placement, their floor planning, placement, then routing, and you after all this you just build the geometric description or this GDS2 file, and then you send it to the foundry. The corresponding chip will be fabricated on that particular foundry, and you will get your corresponding hardware for your system. Whatever that means, I have started with the specification or the design ideas. So, once it has been comes from the foundry, you will get your idea that into reality. Okay. So, now I will just brief about all this what does this particular phase means. So, this design specification, it starts with design specification. So, what are the main design consideration whenever I am considering one design specification? So, at that time what do I consider in my specification? So, the first thing is that this design feasibility. Design feasibility is basically that basically comes with this performance, power consumption and cost. So, performance, power consumption and cost means that comes with design feasibility. I have to check. Why I have to check for this particular things? Performance, it is not that I require or I expect that it will be on the higher side, which cannot feasible, or which as a designer is it is very hard to achieve that particular things. Performance wise, suppose if I say that means ask you to design one 10 gigahertz speed processor. So, is it feasible? Or if I say that that means in nanowatt power consumption processors I need. So, at that time I have to see or I have to check whether that thing is feasible or not. That means, as this is the starting point, what will be my clock speed of the system, what will be the power consumption of the system, what will be the cost per volume of the system. So, all these things are, as it has to be started initially. So, whenever I will set the target, at that time I have to keep in my mind that is that feasible? is it, that means realizable? So, you have to check the feasibility. Okay, people are more greedy, people we need, that means as a person I need more of this to achieve, but we have to be within the limit. Okay. So, that is why whenever we are considering design specification, at that time the design feasibility is the primary concern to be checked. And then design spec. So, design spec should be written in a good starting point, but can be misinterpreted by design team. Okay. So, if I just, that means the specification is basically used in each of these phase, that means where from I am or what I am, what is my target. Specification means what is my, I am setting my target. So, whenever I am working on that to achieve the target, so every time I have to follow or I have to check what target I am having or what target I have to set, what I am basically trying to achieve. Okay. So, that is why it should be documented in a good way. Okay. So, that it has to be that means forwarded, or it has to be known, or it has to be easily accessible to each of the members of your design team. So, it can be written in executable manner, with that means in UML or C language. So, the problem with that is it is very harder to understand and less room, but less room for misinterpretation. Then we have to select this implementation platform. Implementation platform means which design styles we will follow for implementing our design. So, basically the pupils are basically in the initial design phase, they validate their algorithm and the whole system in FPGA. So, once it has been validated, then you can go for the ASIC design, or you can just send it to the foundry. That means your design is, you have checked it is performing finely, or that means you have achieved the corresponding specification, then you go for the foundry. Okay. So, then the another that means things which will be covered in the design specification, that is the development time. That means what is the time for developing the corresponding system hardware. Okay. So, that means from the starting of your system and to the, that means from concept to the reality, how much time you take, that will also be mentioned in the design specification. Then you have to build the RTL specification. So, in the RTL specification means one you have got the specification. So, at that time and you got the specification, you have you have got the information what you have to build or what hardware you have to build. So, everything you have already set. So, at that time you have to build the architecture for that. Okay. So, architecture for that means not architecture, before that you have to, that means first you have to build the algorithm for that. Okay. So that that particular algorithm will be used to build your corresponding hardware or corresponding system. So, then those once this algorithmic verification part is done, so then you can go for that algorithm to the architecture mapping. Okay. So, this architecture algorithm to architecture mapping means that will be described by using some of the block level representation. Okay. So, that means I need this particular component or this particular operators. Operator means this nothing but this adder, subtractor, multiplier. These are the basic components which you used to manipulate or to implement or to describe one particular function. Okay. So, then once this architecture is also finalized, then this architecture will be described using any VHDL or Verilog or using any hardware description language. Okay. So, in RTL specification there should be this IO signals. IO signal means input output signals, then this partition design into functional blocks. So, that means in any particular systems you have this control path and data path, that is the part of the architecture. We will see most of the things. That means here we will cover in this particular course we will cover that things that from this algorithm to the architecture. Okay. So, how efficiently you can do. So, once you have built the suppose the algorithm team they have developed the one algorithm. So, how efficiently you can map that particular algorithm into the architecture, so that you can achieve more of the savings on the power as well as the area, or you can improvise the speed too. Okay. So, that we will see in this particular course. So, after that you have this detailed design. Detailed design means you can choose in different two style, that is in schematic or using HDL language. Any of this you can describe the corresponding, that means once this architecture has been developed, then using using any of these two, schematic or HDL language, language entry, any of this style you can choose for describing that particular architecture into the corresponding hardware. Then you have to do this manage the design hierarchy. Design, you for larger design you have to partition the design. Okay. So, partition you can do in chip partitioning or logic partitioning. So, this is the part of the FPGA design style. I will not much cover on these particular things. So, this is the detailed design specification, or this basically these particular things you require whenever you are designing in or you are following this FPGA design style. Then you have to follow this functional simulation. So, why I need to know about this simulation or this functionality checking of the particular system. So, means whenever I have described the system using any language. So, at that time I have to check, suppose I described or I have built one circuit for adder. So, by mistake if I do any mistake, so at that time whenever I have described, at that time I have just missed somewhere. So, it is now becoming one subtractor, or just it deviates from the functionality of the adder. So, at that time how do I know? So, using the simulation, that means I will put some of the test vector to it and then I will check its output. In adder, if I say that I know 1 plus 1, it will be 2. Okay. So, how do I know? From the beginning I know that 1 plus 1 it will be 2. So, if it is not doing that thing, or if the result it is not giving me 1 plus 1 equals to 2 back. So, if it is if it gives me other value from 2. So, at that time I will check my design that I will know that okay, there is a problem in the particular whenever I have described that means language or the hardware using language. So, again I will check, that means the logic part I have to change. Okay. So, that is why we do functional simulation. And then once this functional simulation is done, then we have to follow this HDL synthesis. So, HDL synthesis means I have described it using language. Now, I have to after that synthesis means what? It has to from the HDL coding, it has to map to the correspond using some of the logic gates. Okay. So, that means you just see that first thing, this translate HDL design files into the gate level netlist. Okay. And all of this, whenever I am converting from logical to the gate level things, that means logical expression from the gate level expression. So, at that time I can achieve more of the optimization to achieve better performance in terms of area, timing and power. So, that is why whenever you are optimizing your design, at the time you can put some of the constant as area constant, timing constant and power constant. So, where from you will get this constant, that means the information about this constant, where from you will get this information? From the specification you will get this information. So, from the specification means I have already know that okay, my targeted clock speed is 1 gigahertz. Okay. So, that means the time, the maximum clock time which is required, that is 1 nanosecond I have to achieve whenever I am designing the system. Okay. The power, if I said okay, it will be let us say 1 milliwatt. Okay. So, 1 milliwatt in the initially I know. So, that constant I will put whenever I will do this particular synthesis, so that this optimization can be done while I am converting from this HDL language to the corresponding gate level expression, logical expression to the gate level expression. So, here the main challenge is that to learn the synthesizable coding styles, then use proper design partitioning for synthesis, specify reasonable design constant and use HDL synthesis tool efficiently. Okay. So, this is all about automated way. So, we will see in the automated way also you can do the optimization, manually also you can do. So, manually you do the optimization and then you just let the tool to do the more optimization on your particular system describe. So, we will see this optimization, manual optimization procedure for this logical expression to the from this HDL expression or this logical expression to the gate level expression. Okay. So, that we will see more how to do that in this particular course. So, then there is this design implementation, this implementation flow is there, that means placement, routing, floor planning, mapping, all these things we have to do in FPGA design style. So, I will not cover that much on these particular things. Then, so initially what I have done, I have done this functional simulation, right. So, here what I have to do, then after this synthesis, I have got to know about this gate level netlist, I have to do this timing simulation. So, in timing simulation what is there? That means, in this particular simulation, in the functionality simulation, no gate delay or net delay is basically included. It only checks whether for 1 I am getting 2 or not for particular array design. Okay. But here you will in timing simulation, here 1 plus 1 is you just put the test vector to the adder, then you obviously will check whether you are getting 2, but after how much time of applying the input, after how much time you are getting the output, that is also be included in the timing simulation. Okay. So, that is the main difference or the basic difference between this functional simulation and this timing simulation. So, here you see this timing simulation, it includes component and wait delays, clock skew, setup and hold times. Though I have put the same vectors as what I have put in the functional simulation, and not necessary if static timing analysis shows no problem. So, that means, whenever we are doing this timing simulation, at the time this static timing analysis is one of the very important parameters in this timing simulation. So, after that there is an option that you have to do this device programming, that means, as I am following FPGA. So, once everything is done, timing simulation is working fine, and then you can go for the device programming part. Okay. So, the common pitfalls or the important points you have to be keep in mind, that is not detailed enough specification. Do not start design entry until all details are clear. A poor design cannot be saved by good code and synthesis implementation constant. Sometimes tough. It is better to let the tool to do the optimization. That means, it is not that the manual optimization is always better. Sometimes you just let the tool to do that, and everything will be clear. That means, whenever your specification will be very much clear whenever you have started the system. That means, your target will be set properly, and then you start working on that to achieve this corresponding target. And always remember that you cannot prove a complex design has no bugs. Okay. And for complex design, verification and redesign is 80% of total design time. So, these are the common things, or the common, that means important points, which will be remembered, or which will be every time whenever you are following each of the phase in your corresponding system design. Okay. So, the steps in this design flow is to you have to describe using HDL, then you have to choose the implementation platform, then this particular thing, synthesis, optimization, mapping, placement and routing. So, this is the steps which are involved in design flow. Okay. So, for today this is it, and next day again we will see more on this particular course. Okay. So, thank you all.